Okay. The next thing I was going to do, the hardest part of your homework is getting the degrees of freedom correct. Because you have some nodes have 3 degrees of freedom, some nodes have 2 degrees of freedom. And so in your assembly process, you have to do something smart. You have to, so can you guys see that? I guess I never looked. What does this look like from your view? Oh, it's okay. Huh? So I'm just going to import the connectivity array, which was given in the assignment, right? And if you remember, if you looked or understood the assignment right, the local node numbering is one, two, three, four, right? It's not in order. It's 1, 2, 3, 4, right? And then I think, is it 5, 6, 7, 8, 9, okay? So in the connectivity array, the first 4 entries are the corner nodes, which are the nodes that have 3 degrees of freedom, right? X, Y, and pressure. And then here, all these mid-side nodes, and the center node is just X and Y. Displacement at X and Y. So what I did is I first I need to know the number of nodes. So the number of nodes are equal to the length of the coordinates. So the coordinates is an XY array, right? So what I did, and this is absolutely not the only way to do this. And in fact, I solved this problem once in Mathematica and once in Python. I think I used a little bit different technique in each one, using the advantage of the language, right? So basically, the first thing I did was I'm going to create something I would call a degree of freedom map. And I'm going to allocate that to be initially a constant array of 3 zeros that has the length number of nodes. Right. So then what I'm going to do is I'm going to say, okay, these are the nodes that don't have a pressure degree of freedom. So because I'm not a very creative person, I come up with really dumb variable names. No pressure degree of freedom. Right? And so this is going to be the connectivity array. Let's see. The connectivity array where I'm going to index all rows, but in the 5th through 9th column, right? So remember, the first 4 have pressure. Right? I want the ones that don't have pressure, okay? And so I get that, all right? But of course, these guys are connected to one another. So let me see if I can see it by inspection. But in other words, those are node numbers, but because the node numbers corresponding to the elements, because the elements are connected to one another, some of those node numbers should appear in 4. One node should appear in 2, because they're mid-side nodes, 2 elements, except for the midpoint node, which would only appear in 1. So I don't know, can I see one quickly? Yeah, right there in the 3rd and the 4th one, there's 21 that appears in both of them. Right? So what I actually want is just the node numbers. I want the union of all those sets, if you will. Right? If you think of all those as sets, I want the union of them. Right? So first thing I can do is there's a command flatten, which will give me a one-dimensional array, and then I can take the union of that guy. Right, so it's a little bit shorter, but now if you were to look through there, you wouldn't see any repeated values. Right? So these are the node numbers that only have 2 degrees of freedom. Right? And so then what I'm going to do is I'm going to index into my degree of freedom map, and I'm going to flag those entries that only have 2, that only have x and y. So the way I'm going to do that is I'm going to say, okay, in the degree of freedom map, the nodes that have no pressure degree of freedom I want to be 0, 0, -1. And the -1 is just a flag. So remember, my degree of freedom map is 0, 0, 0 right now. It's allocated to 0, 0, 0. I'm just going to put a -1 in the arrays that don't have pressure, in the nodes that don't have a pressure term. Right? And so if we now look at what the degree of freedom map is, right? And you can see by inspection it makes sense, right? This is the first node, second node, third node, fourth node, fifth, sixth, seventh, eighth, and ninth all have 2 degrees of freedom, and there's -1s there. All right? So now what I'm going to do is I'm going to fill this array monotonically where they're, because I'm trying to label my degrees of freedom, right? I have the node numbers labeled. That comes from the connectivity array. But remember, my global stiffness matrix is number of degrees of freedom by number of degrees of freedom, not number of nodes by number of nodes. So I want to fill this array monotonically where there are zeros, right? So probably a more slick way to do this, but I'll just do it the dumb way. Just use a loop. Loops are almost always bad in interpreted languages, but if it's something you only have to do once, it's not that big a deal. So I'm going to say if the degree of freedom, if the ith entry of the degree of freedom map equals to 0, then the degree of freedom map at that entry equals to k, and then I'm going to increment k. So that closes the if statement, and then I want to do this for I going from 1 to the length of degree of freedom map. And I haven't assigned k a value. I have to give it something to start. And so now if I look at my degree of freedom map, I didn't do anything.
Should only change the very first one, set it to 0, leave everything else alone, because they're, oh wait, no.
This is just weird.
Could the,
I'm sure I just have a little typo or something. If the degree of freedom map is equal to 0, then set it equal to k, and increment k.
Could you say again why you're doing this? You want to do the total degree of freedom?
I want to put numbers in where all those zeros are, monotonically increasing. So I want 1, 2, 3, 4, 5, 6, 7, la 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 la. 15, 16, 17, 18.
so like not counting the -1.
Yeah.
-4 replacement.
Yeah.
Your DOF map has like 3 rows. Does that work that way? Like it
Oh,
Oh,
yeah. I need,
the tuples aren't.
here we go. That's exactly what's wrong. I need to flatten the degree of freedom map. There we go. Right. So now I have what I want, but I have the minus ones there. Okay. And so then I can get rid of those guys if basically I'm going to use another one of those pure functions. I'm going to say if the value is greater than 0, I'm going to partition the degree of freedom map into 3. So, I mean, let me just show you what that does in case it's not obvious. Right. So I just partitioned it into 3, right? So that corresponds to x, y pressure, x, y pressure, x, y, Node 1, node 1 displacement in the x direction, node 1 displacement in the y direction, node 1 pressure. And on and on and on until you get out here, node 5 only has displacement and no pressure. Okay? And so then what I'm doing in this next step is I'm going to map this partitioned array I'm going to map that partitioned array over this function that selects values, that only selects the values that are greater than 0. So it's going to get rid of my minus 1s. And now I have really what I want. Right? And so I have, these are corresponding to the degrees of freedom. So each grouping is a node, and each subset is the global degree of freedom indice. Right? 1, 2, 3, 4, 5, 6, and then over here 13 and 14. So the reason I think I did this in Mathematica is because you can have ragged arrays. And if you use these functional techniques where you're mapping the arrays over a function, it doesn't matter if they're ragged, meaning it doesn't matter if they're 1 by 3 or whatever. You wouldn't want to do this in MATLAB or Python. Here, in that case, you want to just leave them to be a perfectly squared two-dimensional array. Leave the minus 1s there, in other words. And it just, whenever you're looping it over or whatever, you want to, whenever you encounter a minus 1, you want to do something different, right? Okay. So, yeah, I mean, I think that's my degree of freedom map. So then what I can do with that is, when I want to, eventually I want to use this to assemble into the global tangent stiffness, right? And so in that case, I'm going to compute my element stiffness matrix, like K, the element K, and I want to put that into the global one on the displacements, right? Then I want to compute the element Q, right? Now K is going to have the displacements, it's going to be like for an element K, what's the size of it? An element K. It's 18 by 18. 9 nodes times 2 degrees of freedom. So it's 18 by 18. Right? What is Q? It's the coupling between the displacements and the pressures. So what is it? 18 by 4. You must have already done that. So I could do something like the displacement degrees of freedom are the degree of freedom map. So I'm going to say, using the connectivity array for the first element, but I only want to take the first 2 entries of my degree of freedom map, because those are the x and y locations, right? didn't work. Anyway, so these are the displacement degrees of freedom for the first element. And if you counted them, there'd be 18. And so, you'd actually use this, you'd flatten it, right? If you count 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right? And so I don't have a global stiffness matrix, but what you would do is something like global K, displacement degree of freedom, plus equals KE, right? For the first, this would be inside a loop or something, right? So you'd compute this guy, which is, this is what we've already done for elasticity or whatever, right? So you compute this guy, and it's just the trick is just how you put it in, right? And so then for your pressure degrees of freedom, on the first element, so the first element, but the pressure degrees of freedom only show up in the first 4 entries. And of those first 4 entries, it's the third index, right? X, Y pressure. So those are my pressure degrees of freedom. And so, again, while I don't have one, into the global K, I would have something like displacement degrees of freedom, pressure degree of freedom, QE, right? And then I'd also have the opposite of this. QE transpose. Right. So that's more or less how you do the assembly. It's just, depending on exactly how you coded it, this would be in a loop where you're computing these and sticking them in. And this would be the displacement degree of freedom. You'd probably have this indexed I, right? And you're looping over every element, sticking the things in there.
So can we also combine the element twice? Combining KA and QE, and then assembling by using combined degree of freedom. So combining the first degree of freedom for displacement and the pressure degree of freedom.
I don't know exactly what you're asking, but I'm certain there's 50,000 ways to do it, right? So the answer is probably. Yeah. You could also have all your displacements first and your pressures at the end, right? In your degree of freedom map. You could have all the displacements and then your pressures down below. And there actually might be computational reason to do that, because then you could precondition, you could have a sort of a block matrix, and you could precondition parts of the matrix differently. And it might get faster convergence in a linear solve if you did that. But this is probably the most straightforward way and the most sort of consistent with the notes way.
Also, one more question. Since we have S matrix of zeros, MATLAB gives the warning of the singularity.
Use a sparse data. Well, no. It can't be singular if you apply the boundary conditions.
It just gives the warning and then calculates. It gives the value.
Yeah.
It's also warning.
Also, if you are using sparse data structures, if you convert your matrix to sparse matrices, it may just go right into an integer solve, and it may not give you that error. The last thing, I'm not going to give you the answers, but I'll show you something what they look like. Right, so again, when I said earlier, this is one of those problems that if you get it right, it sort of makes sense, but if you don't, you'll know it. And so here, I'm applying a pressure here, and the displacement's highest right near the wellbore, and it's kind of smooth gradient going away. And later, when the wellbore is slightly elliptical, so later when you plot the stresses, and I actually get a little bit negative pore pressure too. But the values, I think, in the problem statement, I changed them. You should look, I changed them yesterday.
Yes,
Okay, so anyway, the values are kind of made up. It's not really the point. But yeah, so when you plot the stresses, then you sort of, because of the eccentricity of the wellbore, you'll get not perfectly symmetric kind of stress fields. So you should have something that looks similar to that. Any questions?